Our Sun isn't much, compared to other stars in our Milky Way. While it's pretty average, as stars go, it is special to us. The Sun is the source of our night and day. It contributes to the seasons we experience. And it is the source of the energy that both drives our weather and climate systems, and photosynthesis, the source of oxygen and food for life. In this part of our unit, we will learn more about the structure of our Sun, how it produces energy, and how this energy gets to us here on Earth. The central part of the Sun is the core. Here density, temperature, and pressure are all the highest. Like Earth, we have never directly observed the core of our star. The high temperature and pressure found at the core of the Sun allows hydrogen nuclei to fuse together, making helium-3, an isotope of this noble gas. Additional hydrogen isotopes fuse with the helium-3 producing helium-4. The energy produced by this nuclear fusion is the source of the Sun's energy. Energy produced by fusion in the core radiates upward and outward as photons of high-energy light pass through the radiative zone. The radiative zone lies just above the core of the Sun. Light radiation travels as packets of particles known as photons. Albert Einstein and other scientists proved that all electromagnetic radiation has a wave-particle duality, exhibiting properties of both waves and particles. The interior of the Sun is incredibly dense, with many atoms packed closely together. As photons of electromagnetic radiation pass through it, the photons are absorbed and re-emitted by the atoms in the radiative zone. This slows down their passage through the zone quite a bit. The entire journey from the core to the Sun's surface, less than 1,000,000 kilometers, can take up to 1,000,000 years. Once photons reach the surface and head towards Earth, it only takes them a little more than 8 minutes to travel the 150 million kilometers between the Sun and Earth. Above the radiative zone is the convective zone. The solar material here is heated by absorbed photons coming from the radiative zone. This hot plasma begins to rise towards the photosphere, where it cools by transferring energy to that layer. The cooler plasma sinks back down, where it is reheated and rises again, repeating the cycle. These currents of solar plasma are called convection currents. Convection is a common method of heat transfer in fluids, like the Earth's mantle, the atmosphere, and the ocean. Your home heating system heats your home by using convection. Each of the cells seen in the graphic and photograph on this page are the surface of a convection cell in the convective zone. This granulation pattern can be seen even with a relatively inexpensive Coronado solar telescope. Above the convective zone is the photosphere. If you were to safely look at the Sun with an appropriate filter, you would be seeing the photosphere. Eclipse viewing glasses would be safe to use, and getting them early before the total solar eclipse coming April 8, 2024 would be great. The visible surface of our star, the photosphere, has a temperature of around 5,700 Kelvin. This is close to 6,000 degrees Celsius. The surface is dynamic, showing granulation, spicules, filaments, prominences, flares, and sunspots. Solar flares are powerful eruptions of energy from the photosphere. Much of the radiation is shortwave X-ray radiation. When flares occur, they might be seen, but also are detected by Earth-orbiting satellites like GOES. GOES stands for Geostationary Operational Environmental Satellite. Our Sun began the same way all stars do, forming from a vast cloud of interstellar gas and dust known as a nebula. The nebula collapsed from self-gravity and formed a protostar. As the protostar continued to form, heat and pressure in its core increased. Once high enough, this triggered nuclear fusion of hydrogen into helium, and the Sun began its life as a main sequence star. As it ages, it uses up its supply of hydrogen. Someday the Sun will begin fusing helium into carbon and become a red giant. After that, it does not have enough mass to fuse heavier elements, so will shed its outer layers and become a white dwarf. The planetary nebula that forms after the red giant stage of a sun-like star is what is produced when the star sheds its outer layers. You will never have to worry about our sun exploding as a supernova though, it doesn't have enough mass.
Well, way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the centre of that cloud, it gets denser and denser, it gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out, and at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is, as the outer layers of the star get farther and farther from the middle, the force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on it anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang, the outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star, billions of years ago before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually, I think that ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
Pause the video and read over the fate of stars with different masses, from very low mass stars to very massive stars.